Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss law of equipartition energy with proof, application to specific heat and limitations. Let's begin. Statement of law of equipartition of energy. Total kinetic energy of a dynamic system, and that dynamic system consisting of a large number of particles, and these particles are in thermal equilibrium, and these are equally divided among all the degrees of freedom. So the average energy associated with each degree of freedom is equal to half kT, whereas K is the Boltzmann constant and T is the absolute temperature. What is the degrees of freedom? Degrees of freedom is the total number of independent coordinates required to specify completely the position and configuration of a dynamic system. Example, if we consider a particle moving linearly, that is in one dimension, so what are the number of independent coordinates required to describe its position and momentum? That is one coordinate, so its degrees of freedom is 1. Again another example, if a particle is moved along two directions in the sense in two-dimensional plane, so to specify its position and coordinates we require two number of coordinates, therefore its degrees of freedom will be 2. Similarly, if we consider an aeroplane flying, so there will be 3 number of such coordinates required to specify its position as well as momentum, as that aeroplane fly in a 3-dimensional plane. So the number of degrees of freedom will be 3 for that specific system. Similarly, if we taken a thermodynamic system and it consists of large number of particles, and these particles are thermally equilibrium with each other, then the average energy associated with each degree of freedom will be half kT. Now we can prove it. Let me consider a dynamic system, and that dynamic system have f degrees of freedom. Therefore it has f number of such position coordinates and f number of such momentum coordinates. Let f number of position coordinates are x1, x2, x3 up to xf, and f number of momentum coordinates are named as p1, p2, p3 up to pf. Hence the total energy is a function of position coordinates as well as momentum coordinates. So we write total energy E as a function of f number of position coordinates with f number of momentum coordinates. Let me consider ith particle within that of thermodynamic system. So it has pi with the momentum and energy associated with that particle, let ei. So the total energy we can write, that is ei having the particle with energy pi plus e dash f number of position coordinate and f number of momentum coordinates, but that e dash, within that of e dash we exclude the ith particle energy, means ei pi is a function of momentum of pi alone. and that E dash is the function of all coordinates and momentum coordinates excluding that ith particle having momentum pi. So we can easily write E total energy is EI, energy of ith particle, plus rest of the energy excluding that of ith particle. Okay. Now classically the mean energy of that of ith particle is given as EI bar, or we can write EI within that of bracket. Any notation we can use to write the average energy or mean energy of ith particle, that is the total energy divided by number of particles. EI bar is equal to, in place of total energy, that is the energy integration from minus infinity to plus infinity, EI into exponential e to the power minus E by kt into the coordinates dx1, dx2 up to dxf, again dp1, dp2 up to dpf, divided by integration over minus infinity to plus infinity exponential e to the power minus E by kt, then the coordinates dx1, dx2 up to dxf, dp1, dp2 up to dpf, that is the total energy divided by the number of particles. In place of E, we can substitute EI plus EI dash. The substitution we made is equal to integration from minus infinity to plus infinity EI e to the power, here in place of E, that is the EI plus E dash divided by kt, then the coordinates dx1, dx2 up to dxf, then dp1, dp2 up to dpf, whole divided by, again in place of E we substitute EI plus E dash, that is integration over minus infinity to plus infinity e to the power minus EI plus E dash divided by kt into the coordinates dxf, dp1, dp2 up to dpf. Now separating the terms, as we say EI is ith particle having the momentum pi, so we can separate it as the integral from minus infinity to plus infinity EI into e to the power minus EI divided by kt with respect to dpi. Next, another terms, as we exclude that pi from that coordinates minus infinity to plus infinity, simply e to the power minus E dash divided by kt, the coordinates dx1 dx2 up to dxf dp1 dp2 up to dpf whole divided by, again same thing, we separate it, integration from minus infinity to plus infinity e to the power minus ei divided by kt dpi into minus infinity to plus infinity terms as e to the power minus e dash divided by kt dx1 dx2 up to dxf dp1 dp2 up to dpf. Look here, that term and this term will be cancelled with each other. As we say, why we can separate like this? The integral containing e to the power minus ei divided by kt term extend over the position coordinates x1 x2 up to xf and the momentum coordinates p1 p2 up to pf, but we exclude that pi coordinate, and this type of separate integrals are possible. Why? Because e dash is independent of that pi term, therefore we can separate that integral like this. Hence the integrals containing e to the power minus e by kt with these terms are cancelled with each other. So we obtain the integral like minus infinity to plus infinity ei into e to the power minus ei divided by kt dpi divided by integration over minus infinity to plus infinity e to the power minus ei divided by kt with respect to dpi. Okay, now we substitute the value. As we know, energy of ith particle in terms of momentum, that is pi square divided by 2m. So that integral now written as, in place of ei we substitute integration over minus infinity to plus infinity, that is pi square divided by 2m into e to the power minus pi square divided by 2m kt dpi whole divided by, next integration of minus infinity to plus infinity e to the power minus pi square divided by 2m kt dpi 1 by 2m as constant, that is the outside 1 by 2m, integration over minus infinity to plus infinity pi square into e to the power minus pi square divided by 2m kt with respect to dpi whole divided by integration over minus infinity to plus infinity e to the power minus pi square divided by 2m kt dpi. To solve that kind of integral, we use the standard integrals, which is known as the Gaussian integrals. We use the standard integral as minus infinity to plus infinity x square into e to the power minus a x square with respect to dx. Then that integral result as 1 by 2 under root of pi by aq. and integration over minus infinity to plus infinity e to the power minus a x square dx. A is a constant, so pi by a under root. This is the standard integral. Standard integrals. These two standard integrals used to solve these two particular integrals. Look here, x as pi, a is a constant, that is 1 by 2m kt. Now we can use it. So we write 1 by 2m, solving it, pi divided by aq, the constant term, 1 by 2m kt whole cube under root. Next, that integral, again constant, a as 1 divided by 2m kt, x as pi, that result as pi divided by 1 divided by 2m kt under root. So it can be solved like this: 1 by 2m into this under root as solved as 2m kt by 2 into 2 pi m kt under root divided by, next it's written as 2 pi m kt under root. So it's cancelled out. Then mkt 2 cancelled out, cancelled out, so we have only kt. Therefore the average energy EI is equal to 1 by 2 kt. That is proved. We can write EI, that is the mean value of energy, mean value of energy which is associated with energy associated with each degrees of freedom is equal to half kt, and that proves law of equipartition of energy. Law of equipartition of energy. The mean value of energy associated with each degree of freedom is equal to half kt, which is known as the law of equipartition energy, as we write in that of statement. Now that can be proved. Statistically, half kt. Applications of law of equipartition energy to calculate the specific heats of gases. Applications to specific heat of gases. Let we consider 1 mole of an ideal gas at absolute temperature, that absolute temperature let capital T. It has capital N molecules, means we can say that capital N is the Avogadro's number. Therefore, the internal energy of an ideal gas is entirely due to that kinetic energy of its molecules. So, we can write energy, internal energy, that is the total energy, you can say internal energy of 1 mole of gas is that U is equal to that internal energy. Look here, according to law of equipartition of energy, the average kinetic energy associated with each degree of freedom is equal to half kT. As here we consider n degrees of freedom, so it will be half n kT. As we consider capital N number of such molecules, the total internal energy will be capital N times into that. So, we write it N is the total number of molecules or Avogadro's number, small n, the degrees of freedom, from law of equipartition energy. For 1 degree of freedom, the average kinetic energy half kT. For n number of degrees of freedom, it will be half n kT. Since it consists of capital N number of molecules, the total internal energy will be capital N into that term. Therefore, U is equal to half N capital N into K T, or U is equal to half Avogadro's number into Boltzmann's constant, which is known as real gas constant T, where Nk is equal to R, that is the gas constant, universal gas constant for 1 mole of gas. Is the total energy, we can say that is the internal energy. Now, by using the internal energy expression, we can easily calculate the molar specific heat of gas at constant volume and the molar specific heat of gas at constant pressure. Therefore, the molar specific heat of gas at constant volume is Cv, that is du by dt at constant volume, is equal to Cv is equal to d by dt expression of u, that is half nRT with respect to t. Another terms are constant, that is half nr, that is the expression for Cv. Then the molar specific heat of gas at a constant pressure is given as molar specific heat of gas at constant pressure Cp is equal to Cv plus R. Therefore, Cp is equal to Cv value half Nr plus R, which is equal to, taking R as common, that is half N plus 1 . So, Cp is equal to N by 2 plus 1 whole into R. Now, we calculate specific heats of gas at constant volume and specific heat of gas at constant pressure by using law of equipartition of energy. So, what will be the limitations of that of specific heats of gases? Limitations: at a low temperature, in case of quantum mechanics, the expression for specific heats does not hold good. As it is a law, so it must be satisfied in both classical as well as in quantum mechanics. So, therefore it's a limitation to this. So, here with the help of this video lecture, we understand the concept of law of equipartition energy, statement, proof, mathematically we prove it as average energy is equal to half kT for each degrees of freedom. By using that law of equipartition energy, we calculate specific heat of gas at constant volume and specific heat of gas at constant pressure, and then its limitations. So, with this useful and informative notes, let me wind up the session. Thank you.